Alrighty then. All right, we've done an introduction to software engineering, beginning with distinguishing between programming in the small and programming in the large. We motivated the need for the discipline of software engineering, did a brief history of where it came from, and some of its principles and concepts. We also took a brief look at what it means to be a software engineering professional. Okay, today, I'd say we embark upon really the primary content of the course, is taking a look at each of the principal activities in the software engineering life cycle or the software development process. And the way I structured the course is I want to begin with those activities that are most familiar to you. So that's why we're doing these chapters a bit out of order. So we did 1, 2, 3, now we're going to skip up to 9. The implementation activity. Well, what are we going to be doing here? Well, we always want to distinguish whatever activity we do, whatever product we produce. How do we know the process is good? How do we know the product is good? So one of the things we want to do is we want to be able to describe the characteristics of good implementations, particularly good code. How do you know your code's good? And discuss some best practices to achieve them. Those practices are going to be supported by tools. Right? So the tools are going to help us identify weaknesses in our code, and by doing that, also will tell us how to improve the code. Understand a bit more about the role of comments. I don't know how much was discussed in 160 or 161, and what are comments all about? Why do we have them? How do you tell a good comment from a not so good comment? I know when I was teaching 160, we had requirements for documentation, right? And usually had 10 points or so allocated to documentation. And we typically said where you had to have comments, right? Class headers, method headers, sometimes in the internal logic of methods, right? We're all familiar with. Thank you, Mr. Elwood. All right, so we're going to talk a little bit more about the nature of those comments. Let's talk about debugging, okay, and some strategies for debugging. Now, you all have developed strategies for debugging, right, as well as you've developed strategies for testing. Maybe these are seat-of-the-pants strategies. Okay, so I'm going to give you maybe a bit more insight into how you should approach the debugging task and tools that are available to help you. And finally, we're going to take a look at this concept of refactoring and being able to apply some simple refactoring techniques. What do we mean by refactoring? We really mean reorganizing your code. Okay, reorganizing your code. All right, well, a principal goal of software engineering is to produce a working program. Okay, I mean, that's our end objective. Get to the finish line. We've got a product that runs and hopefully satisfies all of the user's requirements. Now, there is a process by which we're going to get to this activity that we're calling implementation. So we're going to define implementation as the act of transforming a detailed design into a valid program. This presumes another activity has already taken place that is referred to here as detailed design. Okay, so we're going to take that detailed design, however it's delivered to us, And detailed design is typically delivered to us using some kind of diagrammatic notation and could be pseudocode, could be an algorithm described using English narrative, or could be a paragraph description. So we're going to take that, transform it into a program using some programming language, together with all supporting activities. Other supporting activities might include putting your source code into a repository, especially if we're in a team environment. So multiple programs can work on the same, let's say, package or the same class. Okay, now I mentioned that there is a presumed preceding activity. Now, detailed design might be done as part of implementation. Well, what might we mean by detailed design? Let's just take this simple definition of detailed design as developing, say, algorithms for methods, or that algorithm might be just expressed as steps, 1, 2, 3. Okay, just English steps, 1, 2, 3. That kind of design could be done as part of implementation. Okay, so someone gives you, hey, here's a class, here are its methods. Okay, so I could give you a little diagram. I think most of you are familiar with some aspect of UML. So I'll give you a little diagram, names the class, shows you the methods, might define the method signatures for you, and then gives a little English description, a couple sentences or a sentence or two. It says, here's what the methods do, or here's the set of class responsibilities, go. So what you might do as the programmer, say, okay, based on this high-level description of this method, I'm going to create steps 1, 2, 3 like I did with the string sorter case study. Develop those as comments and then translate those comments into code. Okay, that is doing detailed design along with implementation. Now, in the ideal, okay, these are typically separate steps and often performed by separate people. But if you do them together, okay, so maybe I hand you this class description and you do the detailed design, the implementation, that's usually faster. That's usually faster because often you don't spend a lot of time on the detailed design. You sketch it out just enough so you know where the code needs to go. The problem with that is if I dole this out like a deck of cards, five programmers on my team, say you do that one, you do that one, you do that one, you do that one, you do that piece, we're going to have 5 designers. Right? So the detailed design I come up with and the code is going to reflect the peculiarities of the individual developers, some of whom might be much more experienced than others. So their design, consequently their code, might be of higher quality than others. So that means we're going to end up with possibly a less cohesive and less organized implementation. That being said, for smaller projects, doing detailed design as part of implementation works pretty well. Okay, clearly it's going to work well for things like the string sorter and assignment 1, or probably any assignment you got in any course that preceded this one. The larger the project gets, the harder it gets. Well, I shouldn't say harder it gets, but the less advantageous it is to let the individual developers do the detailed design. Because what you really want to have is you want to have the same kind of approach, right, to design and to implementation. Okay, writing code, okay, is one of the implementation activities, but it's not the only one. We have to do unit testing. Unit testing is almost always the responsibility of the individual software developer. And what I mean by unit testing at this point is you test a method, you test a class. Okay, testing a class really means you're testing all methods within a class. You might also be responsible for testing a package, which might be a small collection of classes. Okay, that's usually the purview of the individual software developer. That activity is going to be discussed in the next chapter, 10. Also, of course, responsible for debugging your code. Okay, so that's part of implementation. Part of implementation, we'll take a look at this at chapter 11 in a few weeks, is you have to build the code that is written by these independent members of the team into an executable product. You should realize it's entirely possible to take, let's say I've got a product, we'll just take very simple, let's take the quarterback problem from assignment 1. I could have created something that represents the quarterback, and I could have taken something that represents the I/O and something that represents the main method. I could put those in 3 separate classes. I could have doled those out to 3 separate developers. And it's possible to test those classes, even though you can see they depend upon one another, independently. Okay, by faking whatever is needed by the class you're working on. Well, at some point, you need to bring that disparate code together and do testing of the whole product from start to finish. So we need some means to assemble independently developed pieces of code into an executable product. That's part of chapter 11. And once we do that, the product is going to evolve. This is especially true when we use an iterative process. So we need to keep track of the different versions of software that's being developed for each iteration. And we're going to use a code repository for that. I think I mentioned we're going to use Git. So configuration management is also part of implementation. So those are the 4 principal activities besides writing code. All right, now let's talk about good implementations. What do we mean by good? And these are not in any particular order. Readability. You have a good implementation if it's easy for me to read and understand the code. Why is readability important? Please.
In case somebody goes back and reads it, they can understand what's going on.
Yeah, but why?
So
Why do they have to?
In case you leave the company and the code needs to be repaired or updated.
There you
that
go.
person can read it.
Yes, excellent. Okay, because you leave the company, someone needs to take your place, and that code needs to be maintained for some reason. And there are lots of reasons the code might need to be maintained. One is somebody found a bug. Okay, found a bug, and it's in that code. Okay. I don't know if, well, we're going to look at debugging a little later, but one of the principal activities in debugging is comprehending the code. That is, building an internal model of how the code works. Okay? And then what do you typically do? Well, you typically then run through that model, you execute that model, this is one debugging strategy, and find, oh, this logic should do this, but it's doing that. Okay? So if you can't build this internal model, that's what comprehension is all about, okay? Then at least the activity of debugging becomes more challenging. Okay, so easy to read and understand. Maintainability means it's easy to change. Okay, well, if code's any good, it's going to last a long time. If it lasts a long time, it's likely that changes are going to be needed because of changes in the environment in which the code works. And we looked at this when we talked about the quarterback efficiency rating. Said, okay, it works for one quarterback. And that might be enough. Okay? Maybe I'm just doing it for maybe it's just a grade school team. We only have one quarterback, so that's all I care about. But then we talked about, well, gosh, if I want to maintain stats from game to game, okay, well, that's going to require some additional functionality. And if I have multiple quarterbacks, additional functionality. Okay, so you can see how the requirements might change over time. So we have to maintain it. Another reason that maintainability might be important is once I get the code working, and it's working really well, but all of a sudden, and I'm experiencing this, now I haven't had to change the code for this reason, but I had to change the code for another reason. I talked about this water quality information system I've worked on. Originally, it was designed to handle one watershed, the St. Joe watershed. So we have a map, it's got a bunch of pins on it. It's a Google map, a bunch of pins on it for the St. Joe watershed. They came back and said, can you incorporate 3 other watersheds? I said, yes. I said, there's nothing in the definition of the pins represent places where they measure the water quality. There's nothing in the definition of a collection site that restricts you to any particular watershed. All you need to know is the latitude, longitude. You can give it a name and it'll go on the map. All right, so that was good. But they said, oh, but what we want is, we want the different watersheds to appear in outline form with different colors. And we want the pins to be different colors too. That required some maintenance of the code. Because all the pins were the same color, and since I just had one watershed, I didn't bother outlining it at all. So I had to address that. Lucky for me, since I'm a professional programmer, my code was nicely decomposed, so I knew exactly what needed to change to add that functionality. Performance. Another reason, another characteristic of good implementation. Performance, we're typically interested in making the best use of our computing resources. And they usually boil down to time and space. And this is something I think you studied a little bit in 260, probably focused more on time than space. Okay, sorting, I know you studied that probably extensively. Searching, you studied, I think, extensively. Okay, you know, as the number of items to sort or search grows, if you just use simple algorithms, they can be overwhelmed. That is, they can get slower and slower. So we come up with more effective techniques, such as a binary search or maybe quick sort. Okay, studied those. You can see that you can get orders of magnitude improvement in performance. Another thing that's really important in today's applications with respect to performance is network performance. How can I make the best use of the limited network bandwidth that I might have? Okay. That, for example, is why streaming has become so popular. Because we have so much, like take a video. Okay, I created some videos for 160, a tutorial. Now, none of the videos is particularly long. Maybe the longest one's about 15 minutes. But can you imagine waiting at your PC for a 15-minute video to download before it begins playing? No, you wouldn't. You would get so frustrated. Okay, so now what occurs, Okay, with the streaming protocol, you can download a portion of it and you can start playing it while the rest downloads in the background. Anybody have Netflix? Okay, you know that's how Netflix works. Almost everything that does video today streams it. Okay. So it's optimizing the use of limited bandwidth. Traceability. Traceability refers to being able to map the code back to the design. Why is that important? Well, it's important for both correctness and completeness. Okay, I need to know that everything the design said I need to implement, I implemented it. Okay? And assuming that the design was tested in some way and it's shown to be correct, I have to make sure that all the things that the design told me to implement, all those functions and features, I not only implemented, but I implemented correctly. So traceability becomes important, that I can demonstrate this code maps back to that design feature, or that design feature maps into this code. Correctness. This is probably the most important characteristic of good implementation. Okay, so I don't think I need to say any more about what correctness means. And completeness, which goes along with that. I can have all my code correct, okay, but it's still not complete. I forgot to implement some functionality. Okay. Now in here, I summarize this as, with respect to implementation, we want to make it work. That means it runs, so we can test it. Then we make it right, so we do the debugging. Then we want to address performance, so make it fast or make it efficient, make it utilize the resources in the best possible way. And then make it last simply means we want to make sure that the way in which we've done the implementation affords it the best chance of being maintainable. Now let's go into some of the particulars of how we can address those characteristics. One of the best ways to address the readability is in the way in which we write the code. And the way in which we write the code can be guided by style and coding guidelines or requirements. And these are typically organization specific. Now, I know when I taught 160 and 161, we had Java programming and style guidelines. Each organization comes up with a set of probably do's and don'ts. And why did they do that? Well, it's important for consistency. We want to make sure that no matter who works on the code, no matter what the project is, the code always is going to look the same. And it impacts, as I said, readability primarily and maintainability. Now, a lot of programmers chafe at this. Okay? They chafe at this, and it can often be a bone of contention. Typically, it's a bone of contention if the style and coding guidelines are that thick, okay, and you have no tools to help you ensure that you're following the guidelines. Okay. But accommodation turns out to be not so challenging if you've got some good tools available. And if these tools are integrated into your development environment. Now, it turns out that Eclipse, okay, is a very robust and friendly development environment and has some things built in to ensure that code conforms, and I'm going to give you some of these coding guidelines, right now, I don't know if you've discovered this, I'm sure most of you have discovered this, that you can be really sloppy in your spacing and indentation practices and just tell Eclipse, format this code for me, and it does. Right? Everybody know that? Source, format, bam. And you, I think all know that Eclipse can also generate code for you, and the generated code conforms to its guidelines. That's kind of nice too. So you don't have to worry about that. So accommodation turns out to be not so difficult. Now, what do these guidelines usually mandate? Okay? They usually tell you how the code must be indented, how it must be formatted. Tells you something about naming conventions, how your variables have to be named, how your parameters have to be named, how your files have to be named, how your symbolic constants have to be named, how your methods have to be named, all kinds of naming conventions, and language features to use or language features to avoid. So if we want to ensure consistency and highlight meaning, okay, highlight meaning. Well, if we're looking at naming things, okay, in general, okay, what will guidelines attempt to do? Well, they'll have naming rules or guidelines such that the things you name will convey the meaning or intent of the named thing. Like, I look, say, for some reason, I need to represent this inside my program. I probably would not create a variable named x1 to this. I might call it pencil. Okay, you know what I'm saying? And probably wouldn't call it pencil in one place and writing implement in another. Okay? Be consistent. Use the same word for the same concept. Okay? And there's an interesting warning here. If you can't think of a good name, chances are you don't understand the design, or I'm going to back that up, you don't understand the problem either, or the design can be improved. Typically, if you can't name something, or you have to come up with a real abstract name for it, like writing implement, okay, that might mean that someone hasn't taken the time to figure out, are the writing implements we're talking about, are they more like pens or pencils or pieces of chalk or paint brushes? Okay, someone needs to study that more to be more specific. I also put in this little phrase here, whenever possible, you should be choosing names from the problem domain. We already talked about, as we transform, the problem lives over here and our code lives over here. Okay, and there's a great gulf between the structure of the problem and the way it's expressed and the structure of the solution and the way it's expressed. And as much as possible, we like to minimize the intellectual distance. And one way to do that is to choose names from the problem domain. And we discussed this briefly last time in the QBER assignment, quarterback. That existed both in the problem and we could place it in our code. And then we also had those terms, comps and ints and yards and so forth. Well, we see those terms in the domain, we could use them in the program. Another thing they do is, okay, if you want to be descriptive with your name, okay, then the name might turn out to be a noun phrase or a verb phrase. So how do we separate words? Okay. I put the one down here. Java uses this. Okay, the way Java typically separates words is it uses camel case, and so it capitalizes them. Some other languages use underscores. Okay. In general, longer names are more descriptive, but don't go crazy. Okay, just like if you're writing a sentence, there's such a thing as a run-on sentence when you try to put too much content in this single sentence. You might have a name that's too long and obscures its meaning. Indentation and spacing. Well, what's that for? Why do we indent? Why do we use spacing? What's the point? There's blank lines, for example. Blank lines or spacing around operators or between successive parameters. I mean, what's the purpose? Well, one thing that spacing and indentation do for us, and this comes from the real world, by the way, it gives us hints as to what belongs together. It's how our brain operates. The closer things are spatially, the more likely your brain is going to tell you those things belong together. Those are pieces or parts of a related or a single unit. This is also true if you see things that are in a pattern. We humans are very adept at sensing patterns. Okay, we have just wired in our brain patterns for the vertical, patterns for the horizontal. Okay, we're real good at detecting patterns like this, like this, like this. That's why indentation and spacing matter. It helps us to discern pieces of the code that belong together. That then has a great impact on readability. And I just threw up here, I don't know if you've ever looked at a JavaScript, okay, that's been obfuscated. Okay. Meaning all the spacing's been taken out. Okay. And often they've done renaming of things. So you look at it and go, what the heck is that? And it's very difficult to reverse engineer and figure out how the code works. So they purposely reduce the readability. Okay, another thing that's a style issue turns out to be the size of your code units. And for Java, it's mainly what's the size of a method. So in general, it says that the larger the method, the more lines you have in a method, the greater the possibility that something's going to go wrong inside that method. Okay, well, gosh, that makes a lot of sense to me. The more code I write, the more likely I might introduce an error into that code, because there's just more stuff there. But the thing is, when is big too big? When is large too large? When should I take a single method and decompose it into two or more? Now, some heuristics here are, well, look, one page. Okay. Your method, your code should fit on one page or one screen. Now, I put page and screen in double quotes because the size of a page and the size of a screen are relative, right? It's relative to the size of your monitor. It's relative to what font size you're using. The old days, okay, what page meant in the old days is, we used to code and it used to come out on these pages. Okay? So if it was on a page like this, it fit there, it was good. A more mathematical approach uses this concept, what's known as McCabe complexity. And it says McCabe complexity should be less than or equal to 10. What? What's that? Okay, well, we haven't gotten there yet. Okay. But it turns out you can represent the code in your method as a directed graph. Okay, a directed graph. And I think you encountered these maybe briefly in 260. Do you do any graph algorithms? Like shortest path or anything? Okay, so directed graph. You can represent your code as a directed graph. And in that directed graph, you have nodes and arcs. And just think of the if statements, the switch statements, and the loops. All those are represented by nodes that have more than one arc or edge coming out of them. It turns out if you want to compute McCabe complexity, you basically take a look at the decision logic and the iteration logic. Figure out how many of those do you have. Okay, how many of those do you have? So this gets at the idea of how many different ways are there, that is, how many different execution paths are there through your code. And the more execution paths there are through your code, the more difficult that code is to understand, and the more likely it is that one of those paths is implemented incorrectly. So we'll get to that in a little bit, probably next chapter. And error-prone constructs. Okay, error-prone constructs. Nested ifs are error-prone constructs. Okay? In fact, if statements themselves are error-prone constructs. We encourage in the intro sequence to always use block statements for every if. What does that mean? What's a block statement?
Curly braces.
Curly braces. So if, blah, 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 curly brace, logic, curly brace, else, curly brace, logic, curly brace. And we tell you to do that even if there's only one statement after each, right? And why do we tell you that?
That's when you go back and add another statement.
Exactly. You go back and add another statement, all of a sudden you could introduce an error. So that's an error-prone construct. Another error-prone construct is the case statement. Why is the case statement an error-prone construct?
If you don't break,
If you forget to put the break in, what happens?
doesn't run the rest.
It keeps executing, right? Error-prone construct. So you have to take care if you're going to use them. And some of these style guidelines might say, never use nested if, or never use case, or if you're going to use if statements, you must always use curly braces. Now you'll note, I have not gone through any specific rules for style and indentation. We could spend the whole class period going over rules for that. I'm not going to do that. Not to say we're not going to encounter these rules, but I'm not going to do that in class. Because I think such rules are simple enough that you can read and follow them on your own. Okay. Really the same for comments. Yeah?
You were saying in some companies you request that you don't use nested if. Does that mean that the logic of the nested if is replaced in the outer if? Or like how would you determine if, because the point of a nested if is obviously to test both cases, how would you test both cases? Would you just put a longer if statement at the beginning, or how would you do it?
Is how can we avoid nested ifs?
Yeah, like,
Okay. Typically, you avoid nested ifs by using some kind of serial. Okay? So let's just say we have something that would naturally be if, then else. Okay, that's it. Okay? So you have one if condition, do this. Then you have one that follows that, if not condition, do this. Okay, so you're going to be executing both if statements, right? But only one of them will be true. So that's how you can avoid it. Okay. Now another way, by the way, if you can also avoid nested ifs, okay? Because often nested ifs, well, how do they arise? They often arise if you have multiple conditions. Okay, so you have two attributes, attribute A and attribute B. So something has to be true about attribute A, and then you want to test something about attribute B. So that requires nesting. Okay, well, another way to get rid of nesting in that case is you introduce Boolean. Okay, right? So if this test is true on attribute A and this test is true on attribute B, execute this logic. So what you're trading off, by the way, in that case is nesting for what?
Space.
For a more complex conditional, right? Now, if you as a programmer, if you're not comfortable with Boolean logic, then by avoiding the nested if, you could be introducing errors because you don't understand how to construct the Boolean logic, right? Okay. So it's very tricky to determine which is the best course. Okay. So, it depends for me on how complex the Boolean logic is, and also there's a performance hit. Okay, if you're evaluating all those Boolean logic statements, because you have to put them serially, you're taking a slight performance hit than if you're nesting them. But the Boolean logic statements, by the way, if you're adept at reading, they're actually easier to understand than the nesting. Because I always do this. Well, I don't always, but I've done this on occasion. I'll put up some code that looks like this. Then I'll take a statement and I'll say, tell me what's true here. Okay, tell me what's true. And the only way you can do that is
What do you mean?
you got to trace through this logic, don't
Yeah.
you? And keeping track of what's true to get here, what's true, what's true, what's true. Versus, if I'm comfortable with the logic, then I can replace all that with this. And then I point to the same statement, what's true if I get there? Oh, this is true. So there's a trade-off there. In general, we want to avoid too deeply nested logic. Okay? I typically, if I have to go, 3 deep on the nesting, I say, let me find another way to do that. Okay. Another thing, if you want to decrease intellectual distance, if something is stated in the problem, like I did a problem once about how do you know a certain person qualifies for retirement? Okay, and there was something based on age and years of service and something else. But in the problem statement, there was a table. Okay? And the table showed, here are the attributes, and here either the range or it has to be less than this or greater than this. I said, why don't we just take each row of the table and make it one if statement instead of nesting things? Duh. Okay, so that to me decreased the intellectual distance between problem implementation. Right, someone, you have a question? Okay. All right, so let's get back to comments. Should enhance readability, but they could distract from the readability, and they could be wrong. The worst thing that can possibly happen in your code is for the comment not to agree with the code. And typically, what gets out of sync is the comment. Because what are you mainly concerned with when you're developing code?
Code.
The code. Yeah, it's the code. You don't care about the comments, do you? Do you? How many of you, when you're developing a method, write all the comments first? Yeah, I thought so. Okay. Hey, I'm guilty of it too. If I understand something really well, I got to get that code written. Okay? Now, let's talk about the kind of comments that you could have in your code. You want to avoid the first kind of comment. Repeat of the code. Okay, in the classic example of this is you have something like n gets n plus 1. And you have right above it, you have a comment, add 1 to n. Okay, or increment n. Okay. You see that comment gives us no information. Okay. I think Mr. Hoffman is dreaming of those comments.
I might be.
I'm certain you are. All right, so we avoid that. And I think that at one time or another we've all been guilty of that. But this is typically what happens with novice programmers. They fall into this. Secondly, is the comments might be an explanation of the code. Okay? That is, this is what the code is doing. Now the author says, look, typically you have comments like that if your code is really complex. That is, I look at it and I can't tell what it's doing because maybe it has a lot of nested if statements in it and complex Boolean logic, and maybe it's too long. It's got 10 or more of those kind of decision and iteration constructs. And so you've got to explain to me what it's doing. Okay. The author says, okay, sometimes that's helpful, but most of the time that indicates you need to rethink your design. Your logic's too complex. Okay, you need to either find a different algorithm, or perhaps what you need to do is take that logic, which is probably either all or a large part of a method, and refactor it, break it apart, decompose it. Sometimes our comments are markers in the code. They give us meta information. This is very true about Javadoc kind of things. Okay, I got this to-do up here. This is a famous. Hey, I know I've got to do this, so I'm going to put this marker in here, and all these markers are introduced by these @ signs. To do, address case when user doesn't type in numeric data. I know I got to go back and address that case. Okay, so it gives us meta information. Maybe it's another classic one is if you're working in a team and there's more than one programmer that works on a class or works on a method, you might want to put in a meta information, I last changed this code on X. Okay, so you might have a whole series of those markers in the code. The idea is, that really shouldn't be in the code. Those kind of comments should be in a repository. That is, when you change a code, you re-enter it in the repository and you put a comment there. It says, hey, such and such, change this to, add logic to handle non-numeric data entry. Right, a summary of the code. Okay, I would say most of the comments you write are here. This is what the code does. If I would look at, now, I didn't really require this on assignment 1, but if I would go back and review all the comments you made in assignment 1. They would tend to be of this variety. Okay? Here's what the code does. So maybe you have a block of code that consists of those, those equations that compute the QBER. So you say, given the quarterback statistics for the game, following code computes the QBER, something like that. What the code does. That's good. The problem with this is it can lie. That's right, being correct. That used to be what the code does, okay? But I changed the code. I forgot to change the comment. So if I'm reading it, okay, and if you've got some fairly dense code there, I might want to read the comments first to get an understanding of the code, and then go back and take a look at the code itself. Well, if you're lying to me, that's going to cause me to build disparate models in my head, and I'm going to get confused. The best kind of comment you could add in your code is a description of the code's intent. What's the code supposed to do? And the best way to ensure these kinds of comments is to write them first. You write them first. That's why in courses like 160, one of the things we begin with, we have one class, one method, and we typically give the algorithm there. And those algorithms are in the form of comments. And those comments describe what the code is supposed to do. This could be then used, okay, we'll call that detailed design step. I could give that to you. Now you write the code that fulfills that intent. So these comments never go out of style, okay, unless the intent of the code changes. Then we'd have to update these comments. One final kind of comment would be external references. These typically would appear in a class heading or in a method heading. So, for example, the QBER, how do we know how to compute the QBER? Where'd that equation come from? It would have been good to put a reference, in that method header and that class header that says, hey, the QBER, its components and its equation can be found at, this web address. And that would be helpful. All right, so there's comments. So the bottom line is, for comments and general programming style and coding guidelines, you want to use good names. You want to use good indentation and spacing practices. You want good modularization. That is, you don't want your methods to be too small or too large. You want to use good algorithm design so you make best use of your resources. All these things should actually reduce the need for comments. In fact, right-sized methods that follow all these things, you hardly need any comments except what's at the header, because your code should be that easy to follow. And sometimes comments can actually get in the way of reading the code. So use comments, but use them judiciously. Here are some places to look for good guidelines. Okay. This one is the one we're going to follow the most. Okay. Now, let me see if I can get out there, see if this works. Okay. Now, I want to note here that this was developed, you can see, many years ago. But Java, in the sense of style and other coding practices, has not changed that much. So we can still follow these guidelines. So I gave you the link to that. Yeah.
Why would we use the old version if, or is the new version not available, maybe, or, like, these are the old requirements, right? Or,
Well, but there's hardly any, I mean, take a look at, let me see if I can get a simple one here for you. Let me go to contents, and then I want to go to, let's go over here.
Like, is there a newer version of the same information? I think that's what he meant.
You know, I haven't been able to find it. All right, here is, that's what a block comment should look like. Okay, notice the block comment. The begin and end of it are aligned by itself. All right, simple rule, guideline. And there are all kinds of things like that. So we comment how they should be composed, indentation practice, and so forth. They've got the same thing for naming conventions, and they got guidelines for every Java construct. Here's how it should be composed. Now, it looks like a lot, but a lot of it, in terms of the indentation and spacing, is actually handled by Eclipse. You just tell it the format, and you get all this. All right, so that's that. And then there's also this check style plugin. Okay, your next assignment, we're going to do some work with check style. So I just want to show you that page. The link is to this page. Okay, and you're going to download this version. It's version 6.19.1, 6.19.1. That's the version that's accessible from this link. There are actually some newer versions than this. Okay, I want you to get this version. And then I also will note that in order to utilize it properly, you might need to read a little bit about it. Okay, so there's a link here to the check style page. And then there is how to use it within Eclipse. Okay. There's a link here and a link here that give you some guidance how to install and configure and utilize it. Now, if we have a little time, I might do that. And then we also have this. I just wanted to point this out for you. I'm just going to go down here. They got some common practices. Like this one. This one is actually built into Eclipse. It'll whine at you if you do this. Okay. This. Okay, list, stars. Eclipse now wants you to say, hey, tell me what you're going to be storing in that list. Okay, so it doesn't like raw types anymore. We used to be able to get away with this, but we can't now. Okay, it'll whine. By whine, I mean it'll give you a warning, right? It still compiles and everything, but gives you a warning. So there are lots and lots of good practices there. What I'm going to go by is what check style does. If your code passes check style, then it's golden. So let's go back here. So I'm going to see. All right, so check style is open source. Okay, so it's freely available to us. And what check style does, it really codifies, meaning writes in code, a large number of these coding and style guidelines. And there's another couple of, I think this is pointed to by something I already showed you on the previous page. And this one is another one that's similar in nature of how to use it. This you might find helpful because it's got some pictures with it. Right? How to use it within Eclipse. So I want to see, this is always dangerous to try to do something in real time. You're going to have to do this for the next assignment. So I thought, if I can kind of show you how to do it, then maybe that will be helpful. So we're going to try this. All right, so I want to go back here. All right, so I said to download it. All right, so I'm going to download here. And you can see it's the Eclipse. It's the Eclipse. CS stands for check style. So it's the Eclipse check style plugin. All right, so we're downloading it. Okay, this is good. Okay, so let's see, that should be in my downloads folder. Okay, so there it is. Okay, so now what I want to do is I want to integrate this with Eclipse. So I'm going to go over to Eclipse. And over to the help, and I want to install new software. I want to install new software, Eclipse. Let's try that again. Is it going to let me do that? Mr. Reneker, is it not going to let me do that?
I couldn't tell you. To be honest, I tried opening Eclipse.
Let's
but
see.
with Go, and I couldn't even get it to Eclipse on that.
There's some alternate ways to do it also. You can,
I can look for the plugin, I know.
you can drag and drop a link straight into Eclipse.
Not to Neon.
Okay,
Yeah,
yeah. I
that's
saw
It
set
doesn't
up-
work
is
with
that only
Neon.
older versions?
Yeah, if you have the older version, it works like a charm, but it doesn't work with Neon.
Yeah.
And apparently, I can't get this thing.
It might have something to do with admin rights.
Yeah, that's what I'm worried about. That has something to do with admin rights.
Since
Wouldn't it notify you then?
Yeah, it should- yeah, it
Instead of
should
just not
ask
making a window
me.
show up.
So
I mean, sometimes
let's see if it'll do this.
if the program just doesn't have access as an admin, it just doesn't even try.
If you know
Well,
the admin password, maybe you could run Eclipse as an admin.
well, but I don't have the admin password. Do you?
No.
No, do you?
Yeah, but I don't know that I can do that without permission.
No, you don't have to tell me.
No, install it. I don't know if I can install.
Oh,
Since
it's that kind of
Since Eclipse
thing.
is installed in C, I expect, I don't know that I can.
All right, well, okay, guys, then you're going to be on your own here and stuff. But all right, let me just. What's going to happen when you install this new software? You get a dialog, and what you want to do. There's different ways in which Eclipse can locate the software. What you want to select is the archive option. So just click on the archive button and then browse to that file you downloaded. And then once you do that, then you just sort of go click, 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 and it'll get installed. And then once it's installed, when you right click here, one of the options will be check style. Okay, and then you can ask it to check for check style errors. But the other thing you'll want it to do is clear those errors. So yeah, you can work on the code and then run it again. So you will have two items in that menu will be run the check style, check for errors, and clear errors. You can also, from the beginning, you can assign check style, just like here, you'll have an entry in here under properties for check style. And you will be able to associate check style with your project. Okay, so then it will know what actual rules to apply. By the way, when you download and install check style, it comes with, I believe, 3 different rule sets. And you'll want to use the rule set. Let's see, do I have a slide? See if I got a slide there with that. No, I took it out. There's a rule set that's for the Sun coding guidelines that are built especially for Eclipse. So you want to use the Sun Eclipse guidelines, not the Google ones and not the Sun generic ones. So if you want to do something in your spare time between now and Wednesday, see if you can get a hold of check style and implement. That's going to be the first part of assignment 4, by the way. Let's go get check style installed. But if you do it before Wednesday, and if you have any trouble with it, then maybe we can do some troubleshooting in class. Okay, for people who were successful and people who weren't. Yes, Mr. Remick.
I just tried installing it and it doesn't show up in the, so you like click on a project and it,
Did you have to restart Eclipse?
yeah, I restarted Eclipse.
That's weird. So either it didn't install properly.
It didn't throw any errors. It did when I tried dragging the link in the Neon, but I did what you were just saying, I did follow the archive.
And selected it,
Yeah.
and Eclipse plugin showed up,
Yep.
and you went,
And give it the right name and everything.
Could you open up the
When you
browser?
downloaded the
I thought,
the
I could
file,
have sworn I
did
saw
it
that
give you a zip folder
it
that
didn't
had like
list
a variety
Neon in
of
the
jar files in it?
supported
So which
versions
one
of
did you
Eclipse.
click on
What?
to install?
yeah, it's supported, Neon's supported, but not,
Okay.
Neon's not supported in going through the normal way you install Eclipse plugins, and that's go to the marketplace, and then it gives you a link to the upload site, and you just go there, and it does it all for you. And then here it doesn't. All right, so we'll resolve that, Mr. Renick, or maybe you can come by my office hours or something. Okay, so I guess I'm not going to be able to demonstrate that. Maybe between now and Wednesday, maybe I can get some special super permission, because there are other tools I want to show you too that I'm going to need. Yep,
So you said you want version 6.19, right?
yeah, 619.1.
Okay, 6.19.1, all right.
Yeah, which should be, that's what should have got downloaded, I showed you.
Yeah.
Okay? Okay. All right,
Yeah, I
but-
was just making sure, because I didn't hear the 1 the first time, so I
Oh.
didn't know if there was like a 19.0 version, because 19.1, is that not the latest?
No, it's not.
Okay,
There's a version 7.11.
gotcha.
But 619.1 is stable, so I want to use it.
Mhm.
All right, let me talk a little bit about debugging, and then maybe we'll call it a day. So what is debugging? Well, it's locating and fixing errors in your code. How do we know we have a bug in our code? We do some kind of testing. That's the typical way, and the results we get don't match what we're expecting. Sometimes other kinds of errors can be found simply by inspecting the code. I do this a lot, by the way, with intro students' code. Right? They'll come to me, right? My program doesn't work. Okay? Well, show me your code. So, and you get adept at this when you've seen so much code, the same thing. You don't even have to run it. Just describe what it does, and then and I'll just look at it and say, oh, here's the problem. I'll go away and fix that. Okay, so sometimes you can do debugging by just inspecting the code. All right, now, there are typically 4 phases here. First of all, you got to reproduce it. That's called stabilization. Okay, so I run a test, I don't get the right results. Okay, run it again. Make sure that when you run the same test case, you get the same erroneous results. And then what you should do, and I'm actually doing this right now with this other consulting job I've got, we loaded this new set of data, and what I want to say, an old filter doesn't work on the new set of data. Okay. The filter, however, is very complex. I said, okay, let me start building the filter up from ground zero and see where it breaks. So that's what I did. Okay, so that is part of the stabilization, is try to, what is the minimal test case that produces the same erroneous results, and work with that. All right, so that's the first thing. The second thing is now you got to locate the code that produced that erroneous result, and that's usually the hardest step, okay, especially as your code base grows. And this is why it's really important to have cogent strategies at the unit level. Because once you get up to the subsystem level and to the system level, when your test cases are touching more and more code, it gets harder and harder to locate. All right, so once you've located it, you got to correct it. It means you got to change the code to fix the errors. Usually, when you find the statement, or it could be statements of code that are erroneous, you just go like that and say, oh, I know how to fix that. But that's not enough. Then you have to verify. So you got to retest the code to make sure that at least this test case now produces the correct results, and then you can go on with the additional testing for that. All right, so typically 4 steps in the debugging process. Here's a little example. Simple example from physics. So I have an object that's moving on the influence of gravity alone, and these are 2 equations that describe its motion. So if I'm given the initial velocity, I'm given the gravitational acceleration, and then given the time, I can compute the speed and the location, the distance it's traveled, using those equations. All right, so I just want to create a simple program that inputs V naught and T and displays V and S on the system. So here is a test case. Okay, so first 2 things are my inputs, and these 4 are the outputs. Okay. All right, so that's the expected output, but what I get is that. And I just put in red what's wrong. All right, so let's say I run this test case 3 times, and it always fails in the same way. Always get exactly those results. Well, I said, okay, there's something wrong with that 4th line. Now I got to locate it. So here's a strategy. All right, there's something wrong with your output. Where do you look? Okay. Well, there are typically 4 places to look. The first place I look is the code that produces the output. What if I output the wrong variable? Because I often do copy and paste. You know, I hate typing system.out.print, so I'll copy paste. What if I forgot to change the variable? Or sometimes I forget to change the label. Okay, or sometimes when we're dealing with formatting, we forget to format something or we use the wrong format. So the error could be right there. Okay. If it's not there, where could it be? Well, what computed the value that I'm displaying? Look at those statements. And then, okay, there's usually an assignment statement that does that. So I could try to find that, but then what does that assignment statement depend on? So I would then look at the dependencies. So look at the code that computes or inputs the values on which that one depends. And that could be a lot. And then finally, look at the input data. Because sometimes the error is either in the way the data is input, or sometimes the error is actually the data. Okay? It could be the data. I told you to put the data in this way, and you put it in that way, and you flipped V naught and T. Okay? It's your fault. So here is, I just outlined in red, for this very, very simple example, the statements that I would look at. Now often, this is programmer preference. There are two ways you could approach this. You could go from the top down, the forward direction, the way the program would be executed, or you could start from the bottom and go backwards. Okay? So in this case, I started at the bottom. I first looked at, okay, where am I outputting S? Right? Or where am I outputting the fourth line? So I looked here. Okay. Now, there's a comprehension problem here. The comprehension problem is this. Okay. What is S? Horrible name. Okay. But the reason it's S here is why?
Requirements.
Okay, in the problem statement, okay, I'm using the vocabulary of the problem statement. The problem statement wasn't very descriptive, but this is, this is how the math equations are written, so I used S. So, given that I know the problem statement, I know what S is. And so if S in the program represents the same thing, has the same meaning as the problem statement, then I am outputting the correct variable. So I look at this and say, okay, the problem's not there. So let me go back and see how S is computed. Okay? So I would look at this. And I say, okay, I'm going to look at that, and the problem's actually there, but I'm going to ignore that for a second. Okay, I would look at that next, and then I note that the value that's computed for S depends on V naught, it depends on T, it depends on G. So I need to look at those things. Okay, so here's T, it comes in as input. Here's V naught, it comes in as input. Are these read correctly? Okay, that's what I'd be looking. Are they read correctly? Okay. It says enter time. Is time being entered here? So I have to do a program comprehension. Enter initial velocity. Is that the initial velocity? Again, that's a comprehension. Okay, and then the other thing is G. So I have to look at where's G defined. Oh, it's defined as a named constant. Okay, is that given the correct value? Okay, so those are all places for me to look. Now it turns out, and this is an easy one to miss, but it turns out the problem's right here because I've got integer divided by integer, and I'm going to get an integer. So I'm going to get 0 there when it looks like I should get 1/2. All right, so I corrected. Oh, that was simple. Duh, I made that mistake a million times. Okay. So it should be 0.5. And then after I correct it, I'll rerun it, and now I get the result I'm expecting. Okay, so those are a brief overview of the 4 stages. Now we have some heuristics. Some of your methods, some of your modules are going to have lots of errors due to complexity, lots of decision, iteration logic, maybe lots of computations, might be bad design, could be problems introduced by bad implementation. The design was great, the algorithm's great. Okay, you missed a step of it, you misinterpreted a step of it, forgot a step of it, you used a plus sign when you should have used a minus sign. All kinds of things like that. if you find one error in a method, from experience says you might want to do some additional testing on that method because it's likely it has more than one. Code that you add tends to have more errors than existing code. Well, that makes sense because existing code should have been more thoroughly tested. So if you add new code and all of a sudden some test cases are broken, look there first. And then there are some peculiar to you alone. Each developer comes into a project with history. And you should start reflecting upon where your weaknesses are in code development. If I make code, do I make the same kinds of errors over and over again? What is my weakness? You know, am I weak at formatting? Am I weak at knowing when and where to put parentheses? Am I weak in dealing with mixed math expressions? Those kinds of things. Tend to make those, and you should scrutinize your code before even releasing it to testing, saying, let me make sure I inspect my code there before releasing it to testing. Now here's some other things. There are some tools that we can use. Okay. One thing is with respect to new code, this is built into Eclipse. So I'm working on the code, done some testing. Now I'm working on some new code. Eclipse maintains a history, so you can compare one version of your code with the previous version, side by side. So you can see if something went wrong. Well, what did I change since I last touched this code? And it'll show you. That's pretty cool. And of course, we can do some instrumentation. And we talked about using system.out. You can also use this library, log4j. Or there's other logging APIs that you could use. Instrumentation simply means I want to put in my code at various places where I think things might go wrong. I want to see what the state of my computation is, and then compare it to what I think it should be. Interactive debuggers. Okay, and I just said, you have used the Eclipse debugger, right? Because I would say one of the best tools to use in this class would be the Eclipse debugger. And I just said, look, if you're not that familiar with it, you can get some help, and I give you some links. And what's good about the debugger? The debugger does everything that log4j and system.out would do for you. Okay? You can stop execution at any point by dropping a breakpoint, and you can examine the state of the computation, meaning the state of your variables, what's in them. You can also do what? You can also step through the code. So you can stop it at a point where you know everything was good up to here. Now let me step through the code and see, for example, if it's following the right execution path. And let's see how, as I'm following through the code, how's my state changing? Are these variables being computed correctly? Very, very helpful. And then here's some other cool things. I'm going to, can't demonstrate these today, of course, but we're going to take a look at these two things. These checkers, they do static analysis. Okay, so they're inspecting your code. And what they're looking for is error-prone constructs. Things that historically have produced erroneous computations or might have been used in the wrong way. Okay? So for example, this would say, hey, you're missing a break statement. Did you know that? Things like that. So there are two that I've used in the past, find bugs in PMD, and we'll see if we can demonstrate those. If not, you'll be seeing those in your assignment. Okay, so I'd like to do this, but we'll see if it's possible. Maybe we'll start there next time and see if we can demonstrate all these things. If not, maybe I'll create a little video and do it for you. All right, so that's it for today. We'll finish up chapter 9 on Wednesday.